Okay, this video is about a strong acid versus weak acid, trying to find the pH. And so the first question is finding the pH of a 0.5 molar solution of HCl. Now, HCl is a strong acid. So what that means by being a strong acid is that if you had HCl and you put it in water, it's going to dissociate into hydrogen ions and chloride ions. Now, strong acids dissociate completely. What that means, you can demonstrate that by showing something called an ice table, which shows initially what it is, how it changes, and then what it ends up being at equilibrium. And so so how this goes is the initial concentration of HCl is 0.50. Before you put it in the water, the hydrogen ion concentration and the chloride ion concentrations are 0. But once it starts to dissociate, it's going to dissociate completely. That means it's going to go down all the way. So all of it's turning into ions, so at equilibrium, 0% of it is left as HCl. So if this, because of the mole ratio, if this is 1 and this is 1, if the HCl goes down by 0.5, the H plus has to go up by 0.5. And so at equilibrium, you have 0.5. And the chloride ion also goes up by 0.50. So at equilibrium, you have 0.50. Now, the thing is, to find the pH is equal to the negative log of the H plus. And so with a strong acid, you know the H plus. And so something to remember is with a strong acid, now this is only for strong acids, okay, that the molarity of the acid is equal to the hydrogen ion concentration, or hydrogen ion molarity. It's another word for concentration. So if you can remember that, you don't have to really make this ice table. If you know that the acid is 0.5 molar, then the H plus is also going to equal 0.50 molar. So all you got to do is go pH equals a negative log of H plus, so we're just going to put in 0.50. So the pH then equals, if you do the math, it equals 0.30. And that would be the final answer. Now, let's look at what happens when you have a weak acid. Okay, so acetic acid is HC2H3O2. Now, it's a weak acid, but it dissociates a little bit. When you put it in water, it's going to break into hydrogen ions and acetate ions. Now, for this one, we will make this ice table. And so you just draw it like this to make one, and you just go initial, change, equilibrium, and that's why it's called an ice table. And you draw it like this. And so initially, our acetic acid is 0.80. This is 0, and this is 0. Now, the thing is, we don't know exactly how much this is going to dissociate. So we're just going to go minus x. But if this goes down by minus x, this is going to go up by plus x. And so would the acetate ion also be plus x. So at equilibrium, we have 0.80 minus x. This will be x, and this will be x. Now, with a weak acid, you need what's called an acid dissociation constant, better known as Ka. And what that will allow you to do is to figure out the H plus. So to do that, you have to write an equilibrium expression. So to do that, an equilibrium expression is you just write Ka and you go equals. And what it is, it's the stuff on the right side of the arrow. It's the product, so it's going to be H plus times C2H3O2 minus. And so for acids, this is always the way to do it. The products over the original molarity of the acid, so we'll just write H, C2, H3, O2. Okay, now we're going to plug in what we know in terms of x. Alright, so we'll write Ka, but Ka is equal to 1.76 e to the negative 5. That's what's given in the problem. That's going to equal h plus, but we don't know that, so we're going to call that x. And we don't know the acetate either, the C2H3O2 minus, so we're going to call that, it's also x at equilibrium. And we know that the acetic acid, after it dissociates, is going to be 0.80 minus x. Now, here's something that's kind of tricky. If you tried to solve this the way it's written, you could do it, but you would need the quadratic equation, which is a nightmare. So the way to alleviate that is to look at the x on the bottom. Because this acid dissociation constant is so small, that means that acetic acid is barely going to dissociate any at all. All right, so I think it'd be around like 0.4% or something like that, but it'd be very, very small. So this x is so very small that it doesn't really matter. So what you can do is you can drop the x on the bottom. And you can always do this for weak acids when they have a pretty small dissociation constant. So what I'm going to do is I'm going to just get rid of this x on the bottom. I don't need that. So we can drop that, and it makes the math a lot easier. All right, and so now what you can do to solve that is you can just solve for what x is. So I'm going to move the 0.80, I'm going to move that over to the other side, and then I'm going to take the square root of both sides. All right, so if I take 0.80 and I cross multiply it over here, and then I take the square root of that, I end up getting that x is equal to 0.0038. Now, what is x? Well, x is equal to h plus. So now I know my h plus, so now I can just go pH equals a negative log of the h plus. And so pH will be equal to negative log 0.0038. And so the pH that I end up getting is 2.4. Okay, so for weak acids, you can make an ice table, but it's always the H pluses are always going to go up by plus X. So at equilibrium, you're going to have X and X of the anion, which would be acetate. You write an equilibrium expression, which is Ka equals H plus times whatever ion it is. In this case, it was acetate. Okay, and then you divide that by the molarity of the original acid, and then you plug in and solve for x, and x is equal to H plus. So kind of a simplified way of thinking about this, for weak acids, the Ka is always going to equal x squared divided by the original molarity of the acid. Now, if it's a weak enough acid, you can drop that x. And so that's another whole story about dropping the x, but for the problems that we're going to do with these real small Kas, you can always drop the x. And basically, when you get x, the x is going to equal the H plus. And then you can solve for the pH by doing the pH is equal to the negative log of the H plus. Okay, that's how to do one of those problems like that.